Hello and welcome to another video at UPSCprep.com. My name is Ishan. I'm the Science and Tech faculty here. So let's start. Today we'll be talking about physics. So your exam requires you to study some concepts in physics, right? And those concepts are you could say that they are slightly more advanced, right? But they are limited in their breadth, right? So what we're going to do today is we're going to build foundation for those concepts, right? So this is the concept comprehensive lecture in physics foundation, right, meant for your exam. So all this comes from your NCERTs. Like most of the stuff that we'll do today is there in the NCERTs, but all this is basically the most important stuff that you must be reading, right? So we'll be talking about things like types of waves and the phenomena of waves, or what are semiconductors or atoms or laws of motion or types of energy, right? So these are very basic concepts. So anybody who's starting out their preparation, they must be aware of all these concepts in order to understand the more advanced uh, topics that are there in your syllabus, right? So this will be a short class, but yes, important nonetheless from the point of view of having that clarity, having that foundational conceptual base in your preparation, right? So let's start. The first thing that we'll be studying is the laws of motion. So these are Newton's laws of motion that you must remember from your school days. So there are three laws. First law is that object in motion will stay in motion, an object at rest will stay at rest unless an applied force changes it, right? So unless acted upon by external force, an object at rest will stay at rest, right? So that is something that you might have experienced, all this while when you, if you sit in a bus, right, and if the brakes are applied, right, if you are in motion and suddenly the brakes are applied, and you, feel that pushback, right? So that's the first law. Of course, there are other examples. Simply your pen is on the table, it's at rest, right? Unless you apply an external force, it will stay at rest, right? Then the second law says the more force you apply, the faster an object changes its motion, right? So that's the famous equation of F equal to ma, right? So the example of this could be, right, if you see football, if you apply greater force to the football, it will move at a faster pace, right? So those kind of things are your uh, examples for second law. Then the third law says for every action there is an equal or opposite reaction. Again, you can take the example of a gun, or you can take the example of a boat, where if you are getting off from the boat, you will move forward, but the boat might move backward, right? So all these things, that you experience all around in your everyday life, they are mostly following these three laws, right? So these three Newton's classical laws of motion, right? Then there is another force called friction that opposes motion, right? So friction is important from the point of view of the fact that if you're able to move, mostly it's because friction pushes you forward, right? So I mean, we don't want to get into the technical details of all these things, but yes, if you have so you can just understand it like this: if you have a frictionless floor, you won't be able to walk, right? So friction gives you that grip, you could say in simple terms. Then there is balanced and unbalanced forces. So if the forces are balanced, that means that the motion will not change. So basically, if you have an object, if you are pushing it from one side, another person is pushing it from another side, that means that the forces are balanced, so there will be no change in motion for this object, right? On the other hand, if the forces are unbalanced, so this person is pushing at twice the force, so the object will be moving in this direction, right? So that is the meaning of balanced and unbalanced forces. All these things, I think these are pretty simple. Let's move forward. Circular motion, again, it's another type of motion, but this is more important from the point of view of our understanding, right? Because when we study space technology, right, when we study space technology, all the objects in space technology, those are following Not circular motion, yes, but something similar to that, right? So that is why it is slightly more important. So circular motion is when an object moves in a circle, like a car on a roundabout, right? So that is what basically circular motion is, right? And then you see that there are two kinds of forces. One acts inward. So when an object moves in circle, there will be one force that acts towards the center and one force that acts towards the outside, right? So the force that acts towards the center or keeps the objects in a circle, that's called the centripetal force. And the force that someone feels of being pushed outside, that is called as the centrifugal force. So if you just take a small thread and tie a stone to it, right? If you take a thread and tie a stone to it and you try and rotate it, uh, right, what you would feel is um, that something, obviously there's some force that is pushing that stone towards the center, but the moment you know you throw you throw the thread, like or you use um, let go of the thread, uh, right? So let's say that it's moving like this, right? You are rotating it like this, and you just leave the thread. So you will notice that the stone, it is moving in the tangential direction, right? So it's moving in this direction, right? So that is the understanding of centrifugal force. That is the centrifugal force acting, right? So basically there are two forces. One is to pushing objects towards the center, and another is pushing objects outside, towards outside. So these are centripetal and centrifugal forces. All right. Then what is work and what is energy? Work is basically something um, that happens when a force moves something, right? So there's force involved and there is movement involved. That is when you say that you have done some work, right? So like lifting a bag or pushing a box. So all these things can make you tired, right? Because that means that you have done some work. And for doing work, you would need energy. So energy is the ability to do work, right? So whatever work you're doing, the ability to do that comes from energy, right? So there are several types of energy. You could say objects which are in motion, they experience kinetic energy, right? So um, like a moving car has a kinetic energy. Then objects at rest, they are having or you could say energy on the basis of position, right? So if you have a building, on top of that, if you have a ball, that ball has a potential energy, right? So when you push that ball from here, so again, so what happens is that potential energy is being converted into kinetic energy, right? Right. So because the ball comes into motion, right? And earlier it was at rest, the energy was stored here, right? So that energy, stored energy, is called as potential energy, right? It has the potential, right? So potential energy is uh, based on position, and it is the stored energy, like a spring, right? So again, if you have a string, if you stretch a spring, that has the potential energy. If you lose, if you leave it, again it will come back, right? Then you have thermal energy, which is about heat, so energy which is stored in the form of heat. Then chemical energy is energy stored within fuels and food items, so basically chemical. Then electrical energy is derived from electric charges, moving electrons when they conduct current. That is called as electrical energy, right? So one of the things that you should be knowing is that all these types of energies, the energy, they can neither be created nor be destroyed, right? So this is the law of conservation of energy, can neither be created nor destroyed, right? But they could be converted from one form to another. So if you have a fuel cell, right? The question was asked last year on fuel cell. So fuel cell, what it is doing, it is converting chemical energy into electrical energy, right? That is what it's doing. Or if you talk about wind energy, what is wind energy doing? Wind energy is converting kinetic energy to electrical energy, right? So there's a windmill, right? There's a wind blowing, wind has kinetic energy, right? And then you have uh, a station here, right, on the back of that, which has a transformer, and that is converting that energy to electrical energy, right? So those are the kind of ways in which one form of energy you could convert into another form of energy, but you cannot create energy, right? So that is one thing. Okay, so let's now come to gravitation. Now, gravitation is a force that is pulling objects towards each other, right? So if an object has mass, basically that object will have a gravitational pull, right? So no matter how small or big the object is, as long as it has a mass, right, it will have a gravitational pull, right? So, right. So because Earth and other planetary bodies have a big mass, that is why mostly when we talk about gravitation, we talk about those objects. That does not mean that a small object around you will not have a gravitational pull. It has a gravitational pull of its own. It's just that it's too small to be noticed, right? So that's what it is, right? And when we talk about the Earth, you use the term gravity, right? So that's just in reference to Earth. Okay, so that is the understanding of gravitation. All right. Um, Now let's move to Kepler's laws, right? So Kepler's laws explain how planets move around the sun, right? So there are three laws that are there, right? First is about shape of the paths, right? So the planets, they orbit sun in an elliptical path, right? So they have an elliptical path. It's not a circular path, right? So you have a sun like this, and then you have a planet like this. Right, so this is, you can see that it's not a circular path, it's an elliptical path, right? Right, it's an elliptical path. And most of the planets, they will have this elliptical path. Now, the speed increases near the sun. So the planet, when it's closer to the sun, it will move faster as compared to if it's farther away. So here it will move slower, right? And here it will move faster, right? That's the understanding. And the orbit time will increase with the distance, right? So what this means is, right, if you have sun here and you have a planet like this and you have another planet like this, right? So obviously this planet is going to take longer to orbit the sun, right? That is the meaning of orbit time increasing with distance, right? So these are the three laws. These are the three laws that are explaining the planetary motion, right? That they are explaining the planetary motion. So they are called as Kepler's laws of planetary motion, right? So just keep them in mind, just keep these things, these basic ideas in mind, right? Then we come to waves, right? So we have covered motion more or less, all types of motion, right? Now we come to waves, right? So waves, there are several types. Um, on the basis of whether a wave requires a medium. So what's a wave? Wave is just some kind of a disturbance, you could say, right? So what happens is that waves basically uh, are going to transport energy from one part to another, right? So some of the times what will happen is that some waves will require a medium, right, and some will not require a medium, right? So those that require a medium would be called as mechanical waves, and those that do not require will be called as electromagnetic waves, right? So these are two bound distinctions on the basis of whether a wave requires wave requires a medium or not, right? So the sound waves, the water waves, obviously they require medium. In space, you don't hear sound. Why? Because there's no medium to carry that, right? And you could hear sound all around you because there's a medium that can carry that wave, right? Similarly, water waves, they are carried by the water, so that is why they are also something that require a medium, right? On the other hand, light comes from sun, right? And it does not require any medium. Radio waves from satellites, again in space, it's working fine because they do not require any medium, right? That is the understanding. Then on the basis of wave motion, you could define it in two ways, right? So if the wave motion is perpendicular to the energy transfer direction, like ripples on water, it will be called as transverse wave. So just imagine, like, if you have a spring or a rope or a string like this, and you are sitting here, and what you do is you try and move the string in this direction. The string is you kept on the ground. You try and move it on this direction, to and fro, basically, right? To and fro in this direction. What will happen is the string, let me redraw this, right? So let me redraw this. This is the string, right? And you are sitting here and you are just moving the string in this to and fro direction. What will happen is the string is going to move in this direction, right? So you were moving your string in this direction and the wave is moving in this direction. This is what is called as a transverse wave, right? So ripples on water, they also work like this, right? On the other hand, if you have, you could say, if you have a spring like this, right, and you push the spring in this direction, what will happen is you will find that the wave moves in the same direction. So those are called as longitudinal waves, right? So here the energy transfer direction and the wave motion both are in the same direction. So those are things like sound waves in your air, right? So these are basically the types of various waves that you can see around, right? So when we look at light is an electromagnetic wave. It's also a transverse wave. So, right, so it's not like all of them have to be belonging to a specific category. Yes, light is both an electromagnetic wave and also a transverse wave. Similarly, sound is a mechanical wave also and longitudinal wave also. Right. So these kind of things sometimes you can see them pop up in statements in your prelims exam, and these are very basic things, right, which most of the people will ignore, but they are the foundational concepts, right, which you must be knowing. Okay, so that's about the types of waves. Now one of the types of waves that we look at is electromagnetic waves. These are important from the point of view of your syllabus. So electromagnetic waves are made of electric and magnetic fields. They're working together, right? So you have something like this, right? Electric and magnetic fields in all directions, right? What are these? These are electric fields and magnetic fields, right? So these are in all directions and they're working together and they're traveling at the speed of light and they don't need a medium, right? So all your radio waves, microwaves, infrared, visible light, UV, X-rays, gamma rays, all these are example of electromagnetic waves. Now, um, let me just spend a minute over here to explain, like, these waves, all of these waves are extremely important because of their applications, right? So if you look at radio waves, they are used in communication. Even microwaves could be used in communications. They are used in cooking. You would know infrared is used for remote controls, or it is also used for heating, right? So it's mostly associated with heat. Then visible light is all around you, used for seeing objects. UV rays come from sunlight. Again, UV rays has application in treatments. Then X-rays has applications in medical science. Gamma rays has applications in medical science, in nuclear science. So all these waves are extremely important, right? And they're arranged in this particular order of wavelength and frequency. So what's the wavelength and frequency? When you have a wave like this, right? So wavelength would mean the distance between two tops or two bottoms, right? I'm taking the tops over here, right? Right, so these are called crests, right? Right. So the distance between two of them, that will be the wavelength, right? And that will be the wavelength. Okay. And frequency would be um, you take a particular time interval, right? And you count the number of waves traveling in that time interval, right? That's your frequency, right? So the waves, when we arranging it, so this could be like 1 second, right? In 1 second, how much of your wave has passed, right? That's frequency, right? So when you look at this order is in the decreasing order of wavelength. So high wavelength is over here, right? And low wavelength is over here. Okay. And wavelength and frequency are inversely related, right? So if something has a low wavelength, it has a high frequency, right? So it is having a high frequency. Here it has a low frequency. Okay. All right. Right. So the logic is that, you know, obviously, if you have big wavelength, right, then obviously, if you choose 1 second, you might have only one wave that has passed through it. On the other hand, if you have a small wavelength, right, so in 1 second, you can have a large number of waves passing through in the same time period, right? So that is the understanding. That is why they are inversely related. All right. So let's move on to different phenomena that we observe in waves. So one is reflection, that you would know, that bouncing off a surface, a wave comes from somewhere and bounces off, right? So mirror is the best example, right? Mirrors where visible light bounces off. Then diffraction is another example. What is diffraction? Diffraction is when the light, not light, it can be any wave that bends around corners, right? So um, if you're sitting in one room, right? If you are, let's say, sitting in a particular room, and this room has a door, and this is room one, and this is room two. You're sitting in room two, right? And there's music playing in room one. So what happens is that waves, they bend around the corner. So if sound has to reach to you, it has to bend, right? So what happens is the sound waves, right, they will bend on the corners and then they will reach you, right? Basically, they will reach you like this, right? So that happens, um, you know, with all these waves, right? So sound waves, because sound waves usually have bigger wavelength, so they can easily pass through doors and you can easily hear the sounds, right? On the other hand, if you put a torch, if you put a torch, or you just say that if you switched on the lights in room one, if you switched on the lights, that won't mean that room two is also illuminated, right? Maybe there's some part of your room that is having that same light, but the other part will not have that light, right? Because light, it will not get diffracted through a big door that easily, right? So basically, this just means, just focus on the simple things. Waves, when they are bending around corners or passing through a gap, um, they are basically exhibiting the phenomenon of diffraction, right? So basically, you see this classic example is in the light experiment, right? You have a small slit of light, where if you pass it through this slit, which is going to be equivalent to the way around the wavelength of the light, then light will have, exhibit diffraction that you can uh, easily see, right? That is diffraction, right? Then there is interference. So what does interference mean? So interference means that waves combine, creating constructive or destructive effects, which means that maybe if you have one wave like this, wave one, then you have another wave like this, wave two, they combine and they become a bigger wave that is constructive, right? That is constructive. On the other hand, if you have one wave like this, another wave which is in the opposite direction, so this is in the opposite direction, right? And you combine them and they might become a smaller wave, right? That is called as destructive interference. Destructive, right? So basically, if the tops and tops match, right, those will lead to constructive interference. And if the tops and bottoms match, right, those will lead to destructive interference, right? So even if you don't understand this uh, addition, it's just okay to know that, waves uh, which are having, just me exhibit with the simple example of colors, right? If they are having some similar pattern like this, right, then they will have the constructive interference. On the other hand, if the wave is in the opposite uh, uh, direction, like this, opposite phase, you say, right? So this will lead to destructive interference, right? So that is the understanding. Then polarization. So what is polarization? Polarization is when if you have a light like this, right? Electric and magnetic fields like this, and you have a Polaroid, which means that you're trying to restrict light to move only in one direction. So then when you pass it through this slit, the light, it starts uh, exhibiting movement in only one direction. That is called as polarization. So you say that this is unpolarized light, and this is polarized light, right? This is polarized light, right? So that is the understanding of polarization. Okay. So this is used in reducing glare or enabling 3D viewing. All these applications are there. So all these phenomena, they have various applications, right? And all these terms, if you just have a basic understanding, that much is going to be enough. Okay. So polarized light, you could say that, we study in, um, you could say we study this in a particular mission also, right? So there's a specific mission, there where polarized X-rays are being used, right? So so you must have an idea of what is a polarized X-ray, right? That is why we are looking at these concepts. Okay. Then light, it exhibits dual nature, which means that it behaves both like a wave and a particle. So it can behave like a wave when you just saw the phenomena of interference, where it's like a wave, but it can also behave like a particle. In the photoelectric effect, what happens is that light, when it bounces on a surface, it uh, what it does is throws off electrons. So right, so that is an exhibition of the particle nature of light, right? So light exhibits both wave nature and particle nature. This is called as a dual nature, right? This is called as a dual nature of light, and it's very important from the point of view of a lot of technologies, lasers, electron microscopes, and even quantum physics, right? Even quantum physics, that is mostly related to this dual nature of light, right? So that is the understanding. Okay, so then there are atoms. So what is atom? Atom is a tiny building block of every matter. Everything that is made of everything that is around you is made up of atoms. So what is an atom? Atom is basically the building blocks of all kinds of matter. It has a nucleus at the center, electrons that move around it. So there is a nucleus at the center which has protons. It has electrons. Protons are positively charged. Neutrons are neutral, right? And you have negatively charged electrons orbiting around, right? So this is basically what I have drawn is the depiction of an atom from the Bohr's model, right? That is how it looks like the planets are orbiting around the sun. Similarly, here you could see electrons are revolving around the nucleus. Okay, so that's the basic structure of atom, right? So now we come to the next one, which is semiconductors. Now, semiconductors, they are materials. There are sometimes conductors and sometimes insulators. What does it mean? It means that, like you have metal, metal is a conductor. On the other hand, if you have plastic, that is an insulator, right? But there is something in the middle which is called as semiconductor. So what happens is, like a silicon material, like if you have silicon, silicon is an insulator, right? It's an insulator, but when you heat it at high temperature, right? Heat it at high temperature, when it's very hot, it starts conducting electricity. It becomes a conductor, right? So this property is very, very useful in a lot of fields, like in electronics, mostly of all of electronic transistors, mostly your phones, your laptops, all of these, they will have transistors. Those are made from semiconductors, right? Solar panels, computers, phones, all these, they are made up of semiconductors, right? Even diodes, which will let the current flow in only one direction. There could be things like a phone charger, or there could be some protective circuits. All of these, they are made up of semiconductors, and that is why they are very, very important from the point of view of your economy, because it has so many uses in manufacturing of electronic components, right? So this is why semiconductors are important, right? So that's all about the basic foundation in physics that you should be aware of. Okay, so that's all about it. We'll meet next time when we discuss chemistry, right? So that's all. If you have any doubt, you can always contact me, and I wish you all the best in preparation.